Yesterday, we talked about the radiation exchange in the case that they are in the enclosure, but they are all black. And based on this slide, at the end of the class, we talk about the sketching of three surfaces and how do we deal with the radiation exchange. Let me remind you of the terminology that we used. We have Qi to J. This is radiosity. What is radiosity again? Radiosity is the emission plus deflection. From surface I reaching to surface J. Okay, and we have the JI, AI. It is the radiosity total in the unit of watts from surface I. Okay, and we learn about Fij. Fij is Q I to J over Gi AI. So the ratio would be less than 1, equal to 1, in case that the J is covering the surface I. Okay, and we talk about the Qij. Qij is Qi to J minus Qj to I. It's a radiation exchange. And it has the plus sign, means surface I loss heat. Okay, minus meaning surface I gain heat. Okay, and then we have the Qi. What is the Qi again? Well, Qi is heat which must be supplying or taken away from surface I to make the surface in equilibrium with the surface in enclosure. Okay, so example. We talk about free surface enclosure. Okay, this is surface one, surface two actually. And this is surface one, surface two, and this is surface three. Inside the triangle, it is the enclosure. Okay, so we're gonna have the Q1 supplying to the surface to make surface in equilibrium. This is Q2, this is Q3. Okay, so when you supply Q2 to surface, Q1 to surface one gonna make the radiation, and radiation can happen in two direction, two components. One, it's going to be Q I J, and it's going to be Q. I'm sorry, not the I J. Sorry about that. Black first, and then red one. This is Q12, and this is going to be Q13. Okay, because Qij is the exchange. Okay, we call this one radiation exchange. It is a summation of Qi to j and subtract with the Qj to I. Okay, and the same thing. So it's going to be Q2 to I Q3 to 1, Q2 to 1 and Qt to 1, and then they're going to be Q2 to 3, and it's going to be also Q3 to 2. Okay. Actually, I should use the color code here. Let me do it. Oh, sorry. Okay, and then the blue one would be here. Okay, so let's say it's mean that when we take a look at nodal analysis, or it's actually energy analysis. Okay, at surface one, you're gonna have Q1 gonna be equal to Q12 plus Q13, and the green one, Q2 is gonna equal to Q21 plus Q13. I'm sorry. Right is going to be 2, 3. And the blue one, Q3 is going to be equal to Q31 plus Q33. Okay? And because note as Q12 going to be equal to Q1 to 2 minus Q2 to 1. And Q2, 1 is going to be equal to Q2 to 1 minus Q1 to 2, right? So in conclusion, Q12 going to be equal to minus Q21. Similarly, Q21, I'm sorry, Q23 going to be equal to Q minus Q3, and Q31 going to be equal to minus Q13. Okay, get it? Get it? So then, let me point it out. If surface 1, 2, and 3 are black, we learn from last session that Qij going to be equal to sigma, let's say it's going to be EBI minus EBJ over 1 over AI Fij. Okay, when surface I and J are black. Okay, we know about this. So we have the red equation is equation 1, the green equation is equation 2, the blue equation is equation 3, right? So then we're going to have Q1 is going to be equal to EB1 minus EB2 over 1 over A1 F12 plus EB1 minus EB3 over 1 over A1 F13. Okay, this is from 1. And now together with the green equation, Q2 is going to be equal to EB2 minus EB1 over 1 over A2 F21 plus EB2 minus EB3 over A2 F23. Okay, and also the blue one. Okay, Q3 going to be equal to EB3 minus EB1 over 1 over A1 F13, A3 F31 actually, plus EB3 minus EB2 over 1 over A3 F21. Okay. And we have to make a note that we learn A1 F12 gonna be equal to A2 F21. A1 F13 gonna be equal to A3 F31. A2 F21, I'm sorry, F1, A2, F23 is gonna be equal to A3 F32. Okay? By having a tree equation like this, it seems that we can represent the surface with circuit analogy. Surface 2, surface 3, and surface 1. And you're gonna have, sorry, like that. Okay, this is 1 over A1 F12, A1 F13. Okay. And you're gonna have the blue one. This is the 1 over A2 F23. Okay. And then each of the node, it is the EB1, EB2, and EB3. Okay. And if you represent the problem of three surfaces with this circuit analogy, for thermal radiation, you can write, okay, you can represent this by this. So this is nodal analysis at point, at surface 1. The green one is nodal analysis at surface 2. Blue one is nodal analysis at surface 3. Okay. Now, before going further, okay, in circuit analogy from now on, okay, we will treat the surfaces which have the same temperature as one single surface. Okay, so if you have two surfaces, three surfaces, but all of them are at the same temperature, we're going to treat them as if it was still one surface, for example. The problem of heat transfer is you probably have the, surface 1 like that, surface 2 like that, and surface 3 like that. It can be represented if this is T1 equal to 75 degree Kelvin. This is the 500 Kelvin. This is 500 Kelvin. Okay, you can represent because this is T3, this is T2. T2 equal to 33. Well, you can represent it by this. I'm sorry. This is T1 equal to 75 Kelvin, surface 1. And this is surface 2. T2 equal to 500 Kelvin. Okay, so we don't want, let's say, to prevent confusion, we call surface a number of surfaces which has a constant temperature as zone. Okay, so this, we're not going to call it surface anymore. We call it zone. And this is zone 1. This is zone 2. Okay, now zone is surface, all surfaces which is or are at constant or same temperature. Okay, now you know about zoning. Okay, then let's get back. You deal with the representation circuit analogy of the surfaces, but all the faces has to be black. Okay, so the big question is that how about if the surface is not black? What happens? How we find the radiation exchange when surface or zone are not black. Right? How do we deal with it? Let me zoom it in. Okay. because previously we deal with the surfaces when they are all black. But right now, if it's not black, how do we deal with it? Well, we have the white. So let's give the example. Set up the enclosure first. Okay. So I have the enclosure with multiple zone. Okay. And all of them are real surface. Enclosure with real zone or surfaces. Okay. So in that case, let's say you have the surface I, and surface I is at the temperature of Ti, the area is Ai, and most importantly, it has the emissivity epsilon I. Okay? And you know if it is black, epsilon I, epsilon for a black body, is equal to 1. And you have a surface J with temperature Tj, area Aj, and epsilon J. Just for the sake of sample, if you have the zone that you call zone 1, meaning it's at temperature of T1, A2, and A1, and the epsilon 1. Okay? And if you take a look at surface I, what happened at surface I is that it's going to be having the radiation, Ji. Okay? And it's going to have the radiation of Gi. G is a radiation, radiation from something else except from the flat surface of iron. Okay, and we don't know Ji or Gi is going to be which one is going to be larger. Sometimes Ji is going to be larger than the portion of Gi arriving to surface I. Sometimes on the opposite, Gi is greater than Ji. But either gaining or losing energy, you have to sustain you have to make the surface in equilibrium. Surface I has to be in equilibrium. In order to make it in equilibrium, let's set that you have to supply Qi coordinate. Okay? How do you find the relation between Qi, Ji, and Gi? So you make the analysis over here. The analysis over there is going to give you something like this. Qi is going to be equal to emission. This is losing energy from surface I minus part of irradiation on surface I. Actually, to avoid confusing, I can use the irradiation, okay, on surface I, okay? And then, what is it? So it is the Qi going to be equal to emission I, EI. I'm sorry. This is not emission. I'm sorry about that. It's going to be radiosity. Okay. Radiosity I would be Ji AI. Minus the radiation on the surface I would be Gi AI. Reminding you that the unit of G and the unit of J going to be equal to watt per meter square. Okay, so then we factorize the AI out. Okay, and you know that the radiosity equal to emission plus deflection. Okay, and you know that the rho going to be equal to the deflection over total radiation. So deflection is going to be equal to rho. Total radiation would be GI. So it's going to be equal to G. Okay. So we're going to write this radiosity term into this. Emission, this going to be that. Deflection, because we know that deflection equal to rho G, it's going to be rho I GI. Okay? And let's assume that the surface, or the surface on zone diffuse, gray, and opaque. Diffusion gray is going to give you epsilon equal to alpha. Opaque is going to give you tau equal to 0. And you already know that the rho plus tau plus alpha going to be equal to 1. So for opaque, for I is opaque. So it's going to be equal to, because tau is equal to 0. So rho I is going to be equal to 1 minus alpha I, okay, from this equation. And it is a gray and diffuse surface. You're going to have the epsilon I equal to alpha I. Okay. So you substitute J, you substitute rho here first, and then you substitute J into this, and you got this equation. Once you rearrange this equation again, and you know that, you know, 1 minus rho equal to alpha, you're going to get something like this. So this is the final, the result of your analysis from energy balance on surface I. And remember that Ji is defined as the EI plus rho I GI. Okay. And you know that the EI over EBI going to be epsilon I. That's the definition of the epsilon, the emissivity. So in this equation, you're going to have EI going to be equal to epsilon I EBI. Take a note that EBI is going to be equal to sigma TI to the 4. Okay? And then rho I going to be equal to minus 1 minus alpha I. And because of the gray surface, alpha I is going to be equal to 1 minus epsilon I. Epsilon equal to alpha for gray and diffuse. Okay. In that case, okay, You substitute this with this. Okay, and you know it's equal to this, and you rearrange the equation. This is what you're gonna have. Rewrite this equation. You're gonna get radiation is equal to radiosity minus epsilon EBI, epsilon I EBI, or 1 minus epsilon I. So you got the expression for G. Okay, so you substitute this G into at the beginning. Substitute GI to QI. This is what you're gonna have. Rearrange the equation once again. This is what you're gonna have. Okay, so now you got a surface I. Okay, I magnify the surface I, and you have QI going in. Okay, and this QI can be found from this. Okay, and if you take a look, this equation, equation 1, seem to be, once again, seem to be circuit analogy. Let me remind you previously, if I is black, surface I like that, okay, and it has the QI to 1, QI to J, until QI to N. For 3 surface enclosure, you're gonna have the Q1, and this is Q12 and Q13, right? Right? And the node, it has its potential of EB1. Now, because surface I is not black, now, it seems that for the surface, you had a surface like that, it seems to be, has the, here, okay? It seems to have the internal resistance inside the surface. Surface I have the internal surface, internal resistance, the rate, thermal resistance, okay, which across this resistance, it has the EB1 inside, and it has the J1 outside. Okay, so the resistance is 1 epsilon I and epsilon I, AI, in this case is surface 1, right? It's going to be 1 minus epsilon 1 over epsilon 1 A1. Okay. So in that case, if surface 1, 2, 3, just for the sake of example, in relation what you learned from last time, because we end up talking about enclosure of T surfaces, surface 1, surface 2, and surface 3. If 1, 2, 3 are not black, but it's gray, meaning dependent of wavelength and direction. And in fact, alpha going to be equal to epsilon. In such a case, 1, 2, 3 is not black. It's going to have internal resistance, like so. Okay? So this is Q1 going into, this is Q3 going into, this is Q2 going into, but it is a resistance between 2 points. The first point, it is the here, 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 right? It's going to be EB1 on the inside, J1. And it is this is J3 and this is J2. Okay. If 1, 2, 3 are not black but gray, each of the surface or zone, meaning surface with same temperature, has internal resistance, which quantify as 1 minus epsilon over epsilon A. Okay, so this one is going to be 1 minus epsilon 2 over epsilon 2 A2. Okay, and this one is going to be 1 minus epsilon 1 A1. And this resistance is to be 1 minus epsilon 3 over epsilon 3 A3. Okay. Then? Okay, now you understand a little bit more. In comparison with what you have for the black body, remember what you have for the black body? If surface 1, 2, and 3 are black, this is what happened. Okay, make the comparison with what I just wrote down there. Okay. If the surface or zone are black. Okay, so this is black, not black. Okay. Now, as you might guess, this one seemed not to complete yet, right? Because you know that Q1 or Q2 or Q3 passing through some internal resistance from point EB to J. But what happened after J? After radiation from EB go to J is go to where? Okay, now we're gonna see. We're gonna talk about radiation between surfaces. Okay. So we're gonna start with the from the previous section. Previous session. Zone I is surrounded by other zones or surfaces with the same temperature, right? Zone is surfaces with the same temperature, such that a radiation to zone I from other zone, and it can be computed as, well, you have surface like that, and you have the radiosity out, right? But you're gonna have the radiation in. What is this radiation? Well, it from multiple surface or zone inside enclosure. Okay. In that case, you're gonna have the AIGI is gonna be summation of radiosity from some other surface, but reaching to surface side. Okay, meaning that if you have the example of other surfaces, this is other surfaces, we call it surface J. Okay, surface J is going to give the radiation out. Radiation out. Radiation from surface J is the radiosity itself from surface J. Okay, so radiosity from surface J is J multiplied by AJ. But just part of it reaching to this surface. Okay, how much part of it? You have to multiply by FJI. Okay, so it is the equal to AIGI going to be equal to summation of if JI multiplied by AJ, JJ, right? And supposedly you have the n surfaces. J going to be equal to running from 1 to n. Okay, so meaning that if you talk about AIFJI, it's going to be the part of the radiosity from surface 1 to surface I. Okay, I did. It's just try to write this equation in reverse on that. Okay, A1I, A1, J1 plus F2I, A2, J2 plus dot 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 plus ANI, ANJ. Okay, so don't worry, you can write summation in detail. But in operation, okay, I'm gonna take a look at the summation form like that. And then we have the reciprocity relation, which is AI Fij gonna be equal to AJ Fji. Okay, so I change this into this. Okay, AJ Fji is gonna be AI Fij. And rearrange this equation. Now move AI to the right-hand side of the equation. Okay, and because AI seems to be a constant, in the back of summation, it can get canceled with the AI. So you're gonna have GI equal to summation of the Fi, J, JJ, J running from 1 to N. Okay. Remember, the heat balances, the heat balancing on surface, on shown on surface I. You have this at the beginning, right? Reminder, here we go. Here, see? We got this equation, we've seen this one before. Okay, so let's get back there. Because we know Qi multiplied by the equal to AI multiplied by Gi minus Gi. But you know Gi, I just plug Gi in here. This is what I have. Okay. Okay, and this is 1 multiplied by Ji, right? This term. 1 multiplied by Ji. Nothing wrong about it. I just put 1 multiplied by Ji, which still give you the Ji anyway. But 1 is summation of J equal to 1 to N F I J J I, right? Right? We learned about this. Remember? If you don't remember, I'll go back to the slide. Here, this slide. Summation of Fij when j running from 1 to n equal to 1. Okay. Okay. Oh, I'm sorry, I just have j here. Sorry about that. Okay. So I just substitute 1 with this. So this is what I have. Okay, and then I factorize factorize the things out. I'm sorry. I multiply. I make this two summation to become 1. Before that, I multiply AI into the summation. You know that the C summation of A, right, is going to be equal to summation of C multiplied by AI equal to 1 to N, right? I equal 1 to N, is it? So I put the AI inside this, inside that, okay? And my conclusion would be this, right? So it seems, take a look at this thing. It seems that if you have surface I or zone I, your QI is going to go in like that, and it's going to make the summation of Q. It's going to be summation of let's say several decomposing. It has element because it's summation, right? It's so the summation of the term, several term. So QI is going to be have several element, okay? And each of which is going to be each of them is AI, Fij, and Ji minus Jj, when J is 1, 2, n. Okay? And if I write this equation into detail, I probably have this and that, dot, 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 and that, right? QI, separate, decomposing into several pieces, right? And you know what? If I write that in this term, once again, it has, for example, if the free surface for enclosure, let me add the page like that. If there are three surfaces enclosure, what happened? It seems that this is surface 1 because you know that Q1 going to be equal to summation of I equal to 1 to 3 surface, okay? And AI Fij multiplied by Ji minus Jj, right? So you're going to have Q1 is going to be equal to, well, oh, by the way, this is the flat. When it's flat, you already know that's F11 going to be equal to 0. So instead of 3 terms, this one as the F11 going to be equal to 0. This summation going to have 2 terms, which is going to be A1, F12. Oh, I have to write this thing in this form. It's going to be J1 minus J2 over, okay, 1 over A1 F12 plus J1 minus J3, 1 over A1 F13. See, 2 terms, okay? So when it's not black, and you have a surface like that, you have Q going in like that, and you divided the Q into 2 parts, and it is the this is going to be J1 and you enclose on two sides. This is going to be J2. This is going to be J3. See? J1 minus J2, J1 minus J3. And the seems to be, this is the thermal resistance. Thermal resistance. 1 over A1 F13. Okay? Understood? So I already make the assumption that right now we are talking about surfaces for enclosure, right? Let me draw it down for all the three surfaces. Okay. Right down here. And probably use the blue one a little bit further like that. Okay. And then this is surface 3, surface 2 and surface 3. Use this equation for surface 2. You're going to have Q2 going to be equal to J2 minus J1 and 1 over A2 F12 plus J3 J2 minus J3 over 1 over A2 F23, right? Right? Okay. And also you can say Q3 equal to J3 minus J1 over 1 over A3 F31 minus J2, J3 minus J1 over 1 over this is one already shows with 2. Okay, A3 F32. Okay. Providing that because F22 equal to 0. F23, F33 equal to 0. Okay. Now, you know that Q1 going to be equal to Q12 plus Q13. That's the radiation exchange. We already talked about this in the beginning of the class. If you would like to see how I got this equation, browse into the beginning of the class, the last one. You will see what I'm talking about. Okay, and we know that Q2 going to be equal to Q21 plus Q23. Remember? And Q3 equal to Q31 minus Q32. And note that Q12 going to be equal to minus Q21. And Q13 is going to be minus Q31. And also Q23 going to be minus Q32. Right? So this is it. This term is Q21. This term is Q13. This term is this one. 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 Okay? So Q1 going to be coming to, this is Q12. Over here it's going to be Q13. Okay, and you can do the same on the surface 2 and surface 3 is going to have this and the resistance would be 1 over A2 F23. Okay, and you can make the nodal analysis. Okay, so it's going to be nodal analysis. This equation is going to be in, I should use a different color. Okay, this equation is going to be nodal analysis on J. This equation is going to be nodal analysis, oops, no. Nodal analysis, here on this point. So, and this equation is going to be, is it? No, wrong. I'm sorry about that. Here, okay. And Q3 is going to be nodal analysis on the J3. Okay. So, seeing this, take a look. J, and see, J. To complete things up, you will be seeing that if you have three surfaces and they are not black, this is surface 2, this is surface 1, and this is surface 3. Surface 2, surface 3, and surface 1. Okay, each are not black. 1, 2, 3, not black, but it's gray, which is meaning it's diffuse. Right? In that case, each of the surface gonna have internal resistance. And this is except Q3, except Q1, except Q2, okay? And the internal potential is EB. This is EB3, this is EB1, and this is EB2. And the nodal would be J2, and this is J1, J3, and this is J1. And after nodal analysis, which it makes, right? Our analysis is the previous analysis is from the J as a node of the nodal analysis around J. So it's going to have something like this. Okay, and each resistance is that this is 1 over epsilon 2 over epsilon 2 A2. This is 1 minus epsilon 1 over epsilon 1 A1. This is 1 minus epsilon 3 A3. Okay, and what is the resistance over here? This is a resistance from 1 A1 over A3, which is equal to A3 F31. Over here is going to be 1 over A2 F23, which is going to be equal to A3 F32 anyway. So this one is going to be equal to 1 over A1 F12, which is going to be equal to 1 over F2 F21. Okay, so if you make nodal analysis, okay, over here, this is what's happening. This is a representation. Circuit analogy, representation. Radiation exchange. Radiation exchange of three surface. enclosure. Actually, I have to use zone, free zone enclosure. Okay? So, the most important part is not the equation itself. The most important part is try to understand what's going on, what circuit analogy gonna look like. Okay? Let let me let me remind you that if we understand this, if we started out from the surface, let's say if somebody said to you, let me add some page. Okay. If they say, if you have trees of sea zone enclosure and each zone are gray, not black. Show analysis on radiation exchange on each zone. Okay? If somebody asks you this, show analysis of the radiation exchange on each zone, you have to represent the surfaces like that. Always. Like triangle, surface 1, surface 2, and surface 3. Okay? You know that the surface itself is not black. What you learn? You learn that the surface itself has the internal resistance. What is the internal resistance again? Resistance is that 1 minus epsilon, let's say this, that mark it the same way that we just did, 2 and 3. And resistance, internal resistance, 1 minus epsilon over epsilon A, but because it's belong to surface 2, you put subscript 2. Internal resistance is 1 minus epsilon over epsilon A, but this belong to the surface A. So you put 1, 1, 1 there. And internal resistance for surface 3, 1 minus epsilon over epsilon A, but it belongs to surface 3, you put the subscript 3. Okay? And this is going to be resistance in between E, B, 2, and J. Belong to surface 2, put subscript J. Together, this is J1 and EB1. And this is EB3 and J3. Okay? And then each of the Q gonna passing to EB to J. So this is gonna be Q2 passing to, this is Q1, this is Q3. It's gonna be each of the Q gonna passing to EB to its reach J. And then it's gonna, decompose into a number of the heat radiation exchange. Okay, in this case, because you have two other surfaces and each of the surfaces is flat, it's gonna divide it into two. So Q1 is gonna be divided into Q12 and Q13. See, I label it. because it's the radiation exchange from the surface 1. I started Q with subscript 1 and ended up with 2 on one side because the ending is on the surface 2. And on the other side, I started with Q1, 3. 1 is starting point, 3 is the ending surface. Okay? So if I know this Q1, right? Q1 is equal to Q12 plus Q13. But it's already represented by circuit analogy. I know that Q1 is over the internal surfaces, the internal resistance. So it's going to be EB1 minus J1 over 1 minus epsilon 1 over epsilon 1 A1, right? Why? Because it's the Q1 is crossing this, okay, and it's been in between EB1 and J1. There you go. And after that, Q12 is here, and it's across the this node is between J1 to J2. I starting with the on this side, Q12 is going to be J1 minus J2, right? What is it? The thermal resistance. This is thermal resistance, A1 radiation resistance, actually A1 F12. And this is going to be A1 F13, okay? And this is going to be 1 over A2 F23, okay? So I put it here. Now I put the resistance, 1 over A1 F12 plus, okay, this is going to be Q, not Q3, I'm sorry about that. This is going to be Q13. Q13 is over here to over there. A crossing what? It's a crossing potential of, oh, it should be black, J1 minus J3, right? Over, what is the resistance? The resistance is that it's the A1 F13. So I have my first equation. Okay, and then I do the same for Q2. How about Q2? Q2 is going to be equal to Q21 plus Q23, right? This is Q2, and it's going to be Q221, and this side is going to be Q223, okay? And I can detail it up, and it's going to be EB2 minus J2 over 1 over epsilon 2 over epsilon 2 A2 equal to Q21 is going to be J2 minus J1, 1 over A2 F21, right? Because this thing is going to be equal to A1 F12 anyway, right? Plus is going to be J3 J2 minus J3, and it's going to be over 1 over A2 F23. Okay, you got yourself the second equation. And you do the same for the third, J2, J3. And 1 minus epsilon 3 over epsilon 3 A3 equal to J3 minus J1 over 1 over A3 F31 plus J3 minus J2 over 1 over A3 A3 and F32. Okay, you're gonna get third equation. You have yourself three equations for three unknowns. Mostly you end up solving 1, 2, 3, 4, J1, J2, and J3. That's you don't know. Okay, you have to find J1, J2, J3 from this equation. You have three unknown for, three equation. Right? So this is the whole concept. I write it into you, something like this. Oh, this one is wrong. I'm sorry about that. It should be, I'm sorry guys, this should be the EB1 minus J1, EB2 minus J2, EB3 minus J3. Okay, sorry about that, guys. So this is the EB2, this is J2, this is EB1, J1, J2, J3, and EB3. See? This is nodal analysis on J. Okay, nodal analysis on J1 is going to give you this equation. J2 is going to give you this equation. J3 is going to give you this equation. Okay. Wow, now, let's say, let's get to the example, okay? Here are the example of the furnace in cylindrical shape. And it's talk about radiation heat transfer within the furnace. Okay, it gives you the all the relevant dimension, 0, okay, H, 0 and H equal to 1 meter. Okay, you think the the proportion of the figure and the real value, it's just kind of conflict to itself, but you get the idea, okay? Because 0 and H are equal, but in the picture 0 seems to be much less than H. Anyway, so and the surface inside on the top, it's called surface 1. Let me make the cross section like that. Okay, and this is surface 1. And the base is surface 2. Okay, and the rest is going to be the lateral inside surface, surface 3. Okay, and the epsilon 1 is 0.8, epsilon 2 is 0.4, and T1 is going to be 700 degree Kelvin. T2 is the 500 degree Kelvin. The side is black. When it's black, epsilon 3 is 1, right? It's emit the energy out the most. Okay, and the T3 is going to be 400. And they asked us to find the net rate of radiation at each surface. And then when they asked you to find the heat radiation rate, it asks you to find the Q. It asks you to find Q1, Q2, Q3. Okay, the heat which must apply or taken away from each surface in order to maintain the temperature to be constant at each surface. You know that you can find A1, you can find A2, and you can find A3, right? You take a look at the number by itself, by yourself. I will not go into the detail, just to get the idea. You know how to find the area of the circle, which are for A1, A2. You can find the lateral surface A3 anyway, right? Okay. Then, because you know that you have a 9 surfaces, you might not be able to, you might not need all the surfaces, but if you go for all the view factor, it's going to have view factor of the, now, F11, F12, F13, F21, F1, F22, F23, F31, F32, and F33. Actually, there are 9 view factor possible. Okay, but you probably don't need to find all 9 of them. But if you want, you can find all of them too. But you don't have to. Let's say you know right away. Okay, that F11 and F22 is 0. Why is that? Because it's the lip and it's the bottom of the surface, the top surface and the bottom surface. It's flat. Okay, but now F23 is not 0. That's the problem. Okay, so you know that F11, F12 plus F13 is equal to 1, right? You rearrange to find the F13. You know that F11 is 0, okay? How about F12? F12 is the top and the bottom. It's from circle to circle. Well, you go back to the previous slide that I have. Let's say, okay. If you put on the slide on the surface, you're gonna get, remember this plot? Oh no, it's just not the last slide, this slide. Okay. Here we go, right? You can find the Fij, okay? If Rj and Ri are equal, Fij gonna be equal to Fji anyway. Think of it carefully, right? So it doesn't matter which one is on the top, 1 or 2. When you find the F12 is gonna be equal to F21 anyway, because it's a tank. The radius at the top of the tank and the radius at the bottom of the tank are equal in our current problem, right? And let's say you open that graph and you find the F12 going to be equal to 3A. And you know right away that is going to be equal to F21. Why is that? A12 going to be equal to, from reciprocity. You can use the reciprocity relation. A1 F12 going to be equal to A2 F21. A1 and A2 are equal because it's on the top of the tank, the bottom of the tank. So F12 equal to F21. See? Right? So you substitute the F12 in, and you know F11 equal to 0, so you can find F13. I check this one first, you know F2 to 1, you check this one, you know this one, right? And you can find F13. Once you find F13, you remember A1 F13 going to be equal to A3 F31. So you know this thing, you know A1, you know A3, you're going to know F31. So you know this. Okay, 3 more on the list. Okay, so because the fact that F21 plus F22 plus F23 equal to 1, because you know F2 equal to 0, F21 is going to be equal to F3A. So you can find F23. Okay, check. Once you find F23, you know that A2 F23 is going to be equal to A3 F32. So you know this, you know that, you can find the F32. So check. Okay, and the last one, because you know that A31 plus F32 plus F33 equal to 1. You already know these two, so you can find F33 equal to something. Okay, so if you want to find F33, you can do it too, because F31, you already know, F32, you already know. You can find F33 right away. So it's interesting. You want to find it. Okay, so F31 is equal to 0.31. See, this is 0.31. Okay. So on the top surface, let me add the pages. So right now you can represent this surface. This is surface 1, this is surface 2, this is surface 3, right? You can represent always 3 surfaces as the enclosure. Okay, and you know, take a note that surface 3 is back. Okay, so surface 1 is already here, surface 2 is already here, surface 3 is here. And because of the fact that it has the surface is not black, 1 and 2 is not black, so it's going to have the internal resistance, which we can list it as 1 epsilon 2 minus epsilon 2 over epsilon 2 A2. And this is 1 minus epsilon 1 over epsilon 1 A1. See, that's it, right? And this is across EB1. And this is across J2, J1. And this is J2, and this is the EB2, see? And then, because of the tree is black, it has no internal surface, but it has EB1. And flies back, it is the J is going to be equal to, because J is equal to be EB plus G, right? Because it's black, rho equal to 0, right? So J3 going to be equal to EB3 in the sense. Okay, so I would like to draw it into red one. Let's say, okay, here, red one. So this is EB3, which is practically it's J3 anyway, right? But you have the, I use another color, probably the blue one. This is Q3, this Q1, this is Q2, okay? And once it has a radiation exchange, all the radiation exchange has to go through the resistance. See, resistance is still the same, right? So it's going to be, this is 1 over starting point, A2F23. This is A1F13. This is 1 over A1F12, practically, right? And right then, you make the nodal analysis on 3 point, okay? So I pop this up back and I change the color to black. Nodal analysis on J1. What do you have? You're gonna have EB1, I'm sorry, for going to that. Q1 is gonna be equal to Q12 plus Q13, right? Q1 and Q12 and Q13. What is the Q1 again? Q1 passing to EB1 and J1 is going to be EB1 minus J1 over, okay? Internal resistance, epsilon 1, A1, like that. Equal to, how about the 1, 2, Q12 passing through 1 over A1 F12 over from J1 to J2. So it's going to be J1 minus J2 over 1 over A1 F12 plus J1 minus J3 over 1 over A1 F13. See the first equation, okay? And then you do the same nodal analysis on J2. What is J2 again? Let me erase this one first. Okay. So it's going to be Q1, and it's decomposing to this is Q2, I'm sorry. Q2 to 3, and then this one is Q2 to 1, right? Why is the Q2? Q2 is crossing EB2 minus J2 over 1 over epsilon 2 over epsilon 2 over A2 equal to J1 minus J2. I'm sorry, J2 minus back to J1. 1 over A2 F21 plus J3, J2 minus J3, right? On this leg, okay? And it's going to be J2 minus J3 or 1 over A2 F23, your second equation. Okay, take a look, before going to the third surface, let's take a look what we know. Okay, EB1 over here is sigma T1 to the 4th. You already know sigma is a constant. T1, what is T1 again? T1 is the 700 degree Kelvin. T2 is 500 degree Kelvin. You all know about the T, okay? Epsilon 1 you already know, you know. A1, you can find it, you don't know J, okay? You know this, you know that, you know that, you know this. So J, you don't know. This one is sigma T2 to the 4th. You know this, you know epsilon 2, you know A2, you know the T2. So all you have to do is just plug the number in. You know this one, you know that one, and that one. You don't know J1, J2 once again, and you don't know J3 too. So this is the two equation for free unknown. Now you can see that your equation is not enough. You need one more equation. And J1, J2, and J3 is not unknown. It's the unknown. Don't rush to the to answer what the equation posed on to yet. Just reaching to the equation they have at hand first. Okay, and then nodal analysis on J3, or it is the same point J3 and EB3 because surface zone 3 is black, right? Take a look at the top, see? Okay, this is black, and you're talking about this point, okay? Nodal analysis. Okay, so what do you have? So you can't say anything except Q3 equal to Q3 back to 1 plus Q3 back to 2. And it is the Q3 is going to be equal to J3 minus J1, right? Over 1 over A2, A3, F31, that's resistance, plus J3 minus J2 over 1 over A3 multiplied by F32, right? So you got yourself a third equation. Okay, and then take a look what they do. Now, because the surface 3, what they have, okay, after that, see on the third equation, the third equation itself is something that they ask. See, they ask for Q3 2, right? So if you have to take a look at and see if you can solve this equation, well, but you know that J3 gonna be equal to EB3, and J3 is sigma T3 to the 4th, right? So substitute this sigma T3 to the 4th, sigma T3 to the 4th, right? So two equation would have not just two unknown now. It has the three equation with two unknown by J1 and J2 as the unknown, okay? And so all I'm asking is substitute all the number and solving for J2 and J1. And it's seemingly in the book, they already done that, okay? And they said where is it? Oh, okay, here. J1 solving it is going to be 11,418 watt per meter square, and the solve J2 equal to 4,562 watt per meter square. Okay, so I this and copy and put it on the top. Pass. Okay, so solving this, okay, you have the J1, J2, and after that, you plug J1 and J2 inside here and there, okay? J3, sigma 3 to the fourth. This is sigma 3 to the fourth. So you know this thing. Okay, you just plug the number in and so for Q3. Okay, and it's happened that Q3 is the minus 25.5 kilowatt. Okay, how do you find Q1 and Q2 again? Well, take a look at the pictures. Q1 Q1 passing through EB1 to J1 across 1 minus epsilon 1 over epsilon 1 A1. So Q1 going to be equal to EB1 minus J1 over 1 minus epsilon 1 over epsilon 1 A1. So you substitute the EB1 by sigma T1 to the fourth. And you already know the T1 sigma, you already know J1 what it is, you already know epsilon 1 and A1. You just plug the number in. Your Q1 would be something like 25.6 kilowatts. Okay, and then the same thing, Q2 gonna cross from B2 EB2 minus J2 over 1 over epsilon 2 over epsilon 2 A2. And you know this one equal to sigma T2 to the fourth. Now, you already know T2, it's specified, J2 you already saw, epsilon 2 you already know, A2 you already found. So it's gonna be something like minus 2.13 kilowatts. Okay? And if you know it right, it's in equilibrium. Q1 plus Q2 plus Q3 is going to be 0 if you do it right. That's what they found it here. That is right. Okay? Now, I give you the example of the spatial problem. Okay? The spatial problem is that there is the furnace once again. Okay? And actually, it is the port is a long equilateral triangular duct. Okay, figure is already there. And the width of each side is 1 meter. The base surface, it has the base surface, it is not black. Temperature is the 600 degree Kelvin. Okay, the left side is black body, and temperature is the T2, 1000 Kelvin. The right side is well insulated. It has 3 surfaces. Okay, and when it has 3 surfaces, that let me magnify a little bit, because it's black on this side. This is EB2. It's not black on this side. It's at the internal resistance, 1 minus epsilon 1 A1, and is across EB1 and J1. Okay, and this is surface, which is the we don't know it's black or not. But we know that it is the well insulated. When it's well insulated, this is surface 3, right? This is surface 1, this is surface 2. Surface T, if it's insulated, Q3 going to be 0. Okay? Right? And then in between, you're going to have the this side and this side and that side. Right? What is the resistance here? 1 over starting point A2. F starting point 2, ending point 3. Over here, 1 over A starting point 1, F starting point 1, ending point 3. Over here is starting point 1 and starting point 1, ending point 2. See? Just reflect now. Right? So, and you have the Q1 going in like that, and you have Q3 going like that. Okay? And you just, you know, take all the circuit and display is there. See, it's going to be R1 is going to be equal to 1 over epsilon 1 over epsilon 1 A1. And this is 1 over A2 F23, 1 over A1 F13. This is 1 over 1 A1 F12. Okay? And this is Q3. Q3 is supposed to be here, but you know Q3 is 0, so no electricity or the heat flow on this side. Okay, so if you take a look, it is the Q1 going like that, and Q2 going like that. And you know the flow going to be something like this, and it's going to be, you know, combined again, and it's supposed to be out on the node 2. We know right away that the Q1 going to be minus Q2, and Q2 equals to 0. So in this resistance, right, it's going to be in between EB1 and EB2. So my Q1 is going to be equal to, okay, EB1 minus EB2, which is going to give you 1 sigma T1 to the 4th, sigma T2 to the 4th, and you take a look. It's already give you the temperature, okay? On the left-hand side is 1,000 Kelvin. On the base is 600. So T1 and T2 already know. Okay, they ask you to find the heat, which is Q1. Okay, so you have to find the thermal resistance, and the thermal resistance is something like this. So this is EB2, this is EB1, okay? Okay, so heat is going to be something like that. And then it's going to bind to this, right? So it is the, you have to first find series of 2 resistance, meaning this one and this one in series, okay? You're going to have yourself that, right? Reduce the 2 series resistance into 1, and then second, find the parallel resistance, meaning this and that, combine them. Then you're going to have Surface, right? Third, you find the series of the two resistance. This and that, you become TH, right? And put this one into this. You find yourself Q1. Okay? This is this two example. Each of them appear in the past in the final exam before. It's switching back and forth. You must be able to engage with these example. Okay? So study about this example and make sure that you understand what is called. If there is a final exam, it might be a little bit different from example 12.9 and altogether with the example 12.8. But 12.8, 12.9, you need to understand how you got the final answer. Okay? The final exam might not look 100% similar to what appears here. Things might be a little bit changed, but you know how to go. Okay? So that's it for the radiation exchange. I know that in the book there are several more topics talking about this one, but you can read by yourself. I recommend you to read the on the radiation exchange is tuning, okay, but it's not going to be in final exam, but you can read it by your own time in your interest, but because it's about the insulation of radiation, you should know about it, okay. And the second of the chapter, which is not which has not been taught, but you should know about it, is the boiling heat transfer. I give you the extra point if you deal with the boiling heat transfer in your project. Okay. Somebody asked me about the project if it is needed to include the pressure the head loss analysis, meaning fluid mechanics in. Okay. You if you can do so, make the analysis of the fluid mechanics in. That's fine. Great, you superb. If you cannot, you just use the pressure drop. So I'm specifying the pressure drop, that's fine too. There's the pressure drop mentioned in the tube bundle. If you choose your heat exchanger as the shell and tube, when flow over the shell and tube, it's going to drop some pressure. And there's already expression on that. Make sure that you understand what I meant, okay? And if you add the fluid mechanic analysis into this your report, and you add the pool boiling, because the setup the project itself, you have the bath that you boil the water and you dip your heat exchanger in. In that case, you can make the calculation, taking account that there's boiling outside your heat exchanger. If you add these two, I give you a full score. Okay. I will. If you make the analysis right, you're gonna get the 100%. Okay. I give you extra for fluid mechanics analysis and also the pool boiling analysis. Okay, guys, this is the your final lecture. I give you the example of what's going to be the final exam. Let me say again, the final exam might not be 100% exactly like this, okay, but pretty close, okay. I hope you have the study hard. I know that it's been very difficult time for you guys amid the situation, the spreading of the virus like this, and you have to study, you have to do the project, and you have to take the final exam, which must be very difficult. It's difficult for on my side too, but it's not going to be that difficult in comparison with you guys. So We give just only 4 of the final exam, and hope that the final exam you might not copy among the classmates. Please study and do the exam by yourself. Okay. So I wish you a great, a good luck on the final exam and in every subject. And hopefully, if you have some questions, you can throw me in by asking me in the email. Okay, or ask in the line group. I think that there are the line group forming up by Jan Pruk. Okay, you can subscribe on that. Hope you submit all the homework, okay, and the project in time. And good luck on the exam again, once guy. Okay, I'm out. This is the conclusion of the class. Thank you.